Hey guys, welcome back to Car Academy. In this series of video, we are looking into CEC337 DSP architecture and programming of Anna University Regulations 2021. So in the last video, we covered how to install Code Composer Studio, where to download and how to install. We covered few basic stuffs with Code Composer Studio. So in this next series of video, we'll be looking into several problems like convolution, FIR filter, DFT, FFT, dot product, adaptive filter implementations in the Code Composer Studio. Once this is done, we will go and look into some of the applications of image processing and its implementations in Code Composer Studio. Then we'll briefly cover about audio processing and some basic implementation in Code Composer Studio. So in this video, we are going to look into FIR filter and its implementation. Okay, so let's first get started with what is FIR filter. A FIR filter is a type of digital filter characterized by its impulse response, which has a finite duration, meaning it settles to zero in a finite amount of time. The abbreviation of FIR filter is finite impulse response filter. The output of an FIR filter returns to zero after a finite period of time when represented with an impulse input. Okay, so that's the theory part. So I'll first explain how FIR filters work. FIR filters operate by convolving the input signal with a set of filter coefficients, which is basically the impulse response. This convolution process essentially multiplies each input sample by the corresponding coefficient and sums the result to produce the output sample. So if you take a look at this, let me enable the pen. So if you take a look at this, this is basically nothing but input. And here is the h of k, which is nothing but the filter coefficients. So this filter coefficient is nothing but the FIR filter coefficient, and you have basically m samples ranging from 0 to m minus 1. So k ranges from 0 to m minus 1. Similarly, this n ranges from 0 to n minus 1. Okay, so if you have n input samples, you will be basically getting n output samples. So that's basically the theory part. So let me go and explain again. So you have y of n is equal to sum of k is equal to 0 to m minus 1, and then h of k x of n minus k. So what happens is we are having m filter coefficients, and here we have n input samples. So for each input sample, we will be basically going and doing this multiplication operation. So let's first do something like this. So if we have something like, let's say y of 0, I think I can go over the code, and then we can always come back and see if there is something we need to understand in the theory. Okay, so to go to that code, let me quickly disable this pen, exit turn off the pen. Okay, so then what I'm going to do is basically we'll open the Code Composer Studio. In the last video we covered how to open Code Composer Studio. If you have configured properly in the setup Code Composer Studio, I'm going to show you again this process. So it looks like this. So if you have a C6416 device cycle accurate simulator, then you can just say save and quit, Or if you don't have the C6416 device cycle accurate simulator, you can choose that from the right side window. Okay, so choose that, and once you choose that, you have to click this add button. Since I have not chosen anything, I am not getting this add button enabled. Okay, so I have my C6416 device cycle accurate simulator. I'm going to save and quit. It will ask me if I want to start the Code Composer Studio on exit. I will click yes, and upon doing so, the Code Composer Studio window starts loading. As I said earlier, since this is a older laptop, it's taking a bit of time to actually open the Code Composer Studio. Okay, now I got the Code Composer Studio window open. So it looks like this. I have previously created this project. So what I'm going to do is I'm just going to open this FIR filter code. So if you have to do on your own, you will have to basically click project and create new, and then there are two files which you have to add here. One is the linker command file, which I previously showed you. I did not change anything here. Okay, and we have this FIR filter code, which will go over shortly. Okay, so let's take a look at the FIR filter code. So here you can see I have created a structure. This structure has the coefficients, which is nothing but the filter coefficients. We'll see what these are. And then this filter coefficients, this is nothing but the FIR filter order, or basically the number of samples in the filter coefficients. And this is nothing but the input buffer copy, you can say. Okay, I'm creating a FIR filter in this function. What this means is basically this is the structure that I have. The structure name is FIR underscore filter. I'm creating this function FIR underscore filter underscore create, and it's also returning a pointer to the FIR filter structure. Okay, this function accepts two arguments. One is basically the coefficients, and you have the order. Okay, so here what I'm doing is basically I'm creating memory for storing the FIR filter object. Okay, so malloc, I did not do any null pointer check. I'm assuming that the memory is available because this is the only program that's running on the DSP, and it's a very simple program. Ideally, you will have to check if the memory is allocated or not by checking this filter against null. Okay, so I have not done that. I'm just explicitly stating here for this simple program it is okay, but on a production code you will have to always check if the memory has been allocated properly or not. Okay, so I allocated this memory, and then what I have done is I basically also allocated memory for the coefficients, which is the filter coefficients of the FIR filter. So here, as I said earlier, order is nothing but the number of samples in the filter coefficients. So I have to allocate order times size of order. Okay, so I created memory for the coefficients, and then I store the order. I will also have to copy the coefficients. Before that, I'm also creating a memory for the buffer. Okay, so all these have been created here. Now I'm copying the coefficients that came as an argument to this function to the structure variable filter coefficients of I, and the input buffer I am assigning all that to 0 because that's something we'll get in future when we call or when we get the samples. So the FIR filter, let's say you are getting something from the microphone and you want to do some FIR filtering. As you talk, you get the samples, right? So we'll be filling this buffer soon, but for now I have initialized all the samples to 0. And then finally I'm returning the filter, which is basically this one, the one that we allocated in this function. Okay, so then I have two functions, FIR filter apply and FIR filter free. FIR filter free is nothing but we have done 3 memory allocations in this function. So basically when we close this program or when we stop this program, we will have to free all the memory that we have allocated. Okay, so I have done basically free filter coefficients, free filter buffer, and free filter. Okay, so that's all. And I also have a helper function to print the array elements here. So this is nothing, but we'll see what it does. But it's basically taking this array and array length, it just prints the number left to right in a single line. Okay, now let's go and see. Okay, so here's the FIR filter coefficients. I have the coefficients as 1, 2, 4, 2, and this is nothing but a low pass filter, or something like it blurs the contents of the image if we apply this filter to a 2D image. And I find the order basically by computing the size of this filter coefficients divided by size of each element. So size of this array would be 20 bytes, and size of each element will be 4 bytes because size of int is 4. I call the FIR filter create function, which is nothing but the one that we saw earlier. So I pass this filter coefficients, which is nothing but this, and I also pass the order. So it creates that filter, and finally I get that created filter here. I'm also assigning an input signal here, 1, 2, 3, 4, 5. So I calculate the x length. So here I'm just printing the input signal, I'm printing the coefficients, and I'm allocating memory for the output, okay, which is basically the y. So I allocate memory for y, and what I do is for each of the element in x, I call FIR filter apply by passing that element. So I have the filter which is created here if using the FIR filter create function, this one. I pass that, and I also pass x of I. Basically each sample I call this FIR filter apply, and I store the result in y of I. Okay, and when we complete this for loop, we'll have all the output samples. I'm printing the output samples here, and then finally I'm freeing this memory filter. I'm also freeing the memory allocation that we did in this line. Okay, so and return 0. So let's take a quick look at the output before we go and take a look at the FIR filter apply function. Okay, so I built the code. Now you know how to run this. So in order to build the function, you will have to click this button, rebuild all, or you can also click incremental build. And in order to run this program, we have to click this run button. So as soon as I click the run button, you can see the input signal 1, 2, 3, 4, 5, filter coefficients is 1, 2, 4, 2, 1, and output signal is 1, 4, 11, 20, 30. So now let's go and take a look at the FIR filter apply. So FIR filter apply, what we are doing is we are basically taking one sample at a time. First, let's take a look at this for loop. So what we are essentially doing is you have this order, and here what we are doing is in this function, this is a very simple function. We are assuming the input sample and the filter coefficients have the same length. Okay, so if it's a different length, we'll have to slightly modify this program, but for now this is more for the understanding. So once you understand that, you can basically implement the FIR filter in a much more generic way. So what we're doing is basically we are multiplying the filter coefficients with the input signal. Okay, so the input signal, as soon as you get the first signal, which is basically the input, that will be stored in the buffer of 0. Okay, so for the first time, you know, we initialized all the buffer contents to 0. So this is nothing but you're left shifting the signal. So basically whatever was there in I-1 will store it in I. It goes, so we start from the order -1, which is here order -1, here it will be order -2. So we take the contents from order -2 and store it in order -1, and then we decrement I, which is basically order -2, and we'll take the contents from order -3 and store it in order -3 or -2. Okay, so it goes on, and finally at the location 0 or index 0, we store input. Okay, so for the first time you will only have valid content at buffer 0. We multiply that with the coefficient. So now you can see, let's take this example and go back to the whiteboard and do the math. Okay, so we should basically get this 1 4 11 20 30. Okay, so let's go and do that math so that you understand what we actually did here. Okay, so I think you might have understood by now how this works. So let's take a quick look. Turn on the pen. Okay, so our h of n looks like this: 1 2 4 2 1, and our x of n looks like this: 1 2 3 4 5. Okay, so what happens is we first get this sample. Okay, so this sample will have to be multiplied with this FIR filter coefficients. So what happens is, we are going to compute y of 0. So we only have one sample. So this sample, what happens is you do 1 2 4 2 1. You multiply this with 0 0 0 0, and you got the first signal 1. So when you multiply this, what happens is 1 times 0 is 0, plus 0 times 2 times 0 is 0, plus 4 times 0 is 0, plus again 2 times 0 is 0, plus 1 times 1, which is equal to 1. So we have our y of n, the first value, as 1. Then let's go and calculate y of 1. So which is nothing but you get 1 2 4 2 1, which is the filter coefficient, and then here what happens is we got the second signal now. So what we do is we basically move this element to here, this element to here, this element to here, and this element to here, and we store the new signal here, which is 2 in this case. So what happens is you store 0 0 0 1 2. Okay, now let's multiply 0 plus 0 plus 0 plus, you have a 2, and then you have another 2, which is nothing but 2 plus 2 is equal to 4. Okay, so similarly if you do for y of 2, you will get 0 0 1 2 3. So when you multiply that with this whole with this whole and add it up, you will basically get 0 plus 0 plus 4 plus 4 plus 3, which is 11. Okay, we'll say if this is the correct output or not. So then we again shift it 0 1 2 3 4. So when we do this math, we have 2 plus 8 plus 6 plus 4, which is 20. And finally here we have for y of 4, which is 1 2 3 4 5. So that is equal to 1 plus 4 plus 12 plus 8 plus 5. So here you have 30. So our y of n is basically equal to 1 comma 4 comma 11 comma 20 comma 30. Let's go and check what we have in the Code Composer Studio. So you can see it's basically 1 comma, you can see we got the same output 1 comma 4 comma 11 comma 20 comma 30. So that's a very basic simple example implementation of FIR filter in Code Composer Studio. Obviously you can implement the same in assembly language. You can optimize this program. This is a very simple implementation. If you want to also, as I explained earlier in the previous video, you can take a look at the mixed mode and see how each of our C program statements got converted to the CEC337 DSP assembly. Okay, so you can also understand how each C statement translates to the DSP assembly. Okay, so if you like this video, subscribe to this channel. We will be doing multiple implementations of various signal processing algorithms in Code Composer Studio. So in this video, we covered FIR filter implementation. In the upcoming video, we'll implement discrete Fourier transform, convolution, and many other algorithms. So share this useful content to your friends. We will learn and we'll do more of the signal processing stuffs in this video, in the upcoming videos. Okay, so till I come up with the next video, I'm signing off. Thank you.